Chapter 1 deals with the solution of linear systems. The first part of the chapter deals with direct methods, i.e. Gaussian elimination. The last section with iterative methods. Gaussian elimination is a process you're no doubt very familiar with, and in fact the way we're going to implement it on the computer is very similar to what you learned in matrix algebra, with one important difference. So let's review. We'll assume always square linear systems, otherwise you're probably not going to have a unique solution. So we'll assume n equations in unknowns. The Gaussian elimination process is you go column by column, starting with the first column, knock out everything below the diagonal in the first column by taking multiples of one equation, one row, and adding it to the others. And as you learned in matrix algebra, if one of your diagonal elements, the pivots, happens to be 0, of course you have to switch. You can't use 0 to knock out the elements below it, so you have to switch rows. If you're doing the calculations on a computer, in other words with not exact arithmetic, then it's important to switch rows not only when the pivot is 0, but when it's close to 0. And of course there are a lot of possible strategies for deciding when to switch rows. The one that's by far most popular is called partial pivoting. That avoids having to decide how small is too small. You simply look at all the potential pivots, which means if we're working on the ith row, trying to knock out everything, or ith column, trying to knock out everything below the ith column, I can switch the ith row with any row below it. I can't switch with the row above it because that would destroy the zeros in the previous columns. But I can leave the ith row where it is, or I can switch it with any of the potential pivots below. And partial pivoting simply says we'll take the largest potential pivot in absolute value and switch with that. And we'll see that it's the amount of extra computer time in switching rows is negligible anyway for large n, so it doesn't cost us anything to switch rows essentially. So we might as well switch and bring the biggest potential pivot in absolute value up, and generally the bigger the pivot is, the better as far as round off error is concerned, so we'll just bring the biggest pivot and going up. Now if all of the potential pivots, that is aii through ani, if they're all exactly 0, then you have a singular linear system and you have to give up. Otherwise, we'll just bring the biggest potential pivot up there and keep going. And eventually we reduce it to upper triangular form, which is the point of all this. That gives us a last equation which involves only one unknown, a(n) xn equals bn. So we solve for xn, then we go back, do back substitution, solve for xn minus 1, and so forth. So there's a Fortran and MATLAB program in the book that implements Gaussian elimination exactly as we've discussed it, called DLINEQ. First there's the forward elimination. I goes from 1 through n minus 1. I picks the column, only go through the n minus first column because there's nothing below the diagonal in the nth column to knock out. So for each column I, we find the biggest potential pivot, and if the biggest potential pivot is 0, we give up, otherwise we switch. So here we've discovered that L is the row with the largest potential pivot, so we want to switch the rows L and I, switch those there. Then we also switch the BL and BI, the right hand sides have to switch also. Then J goes from I plus 1 through n. That picks the element below the diagonal in the ith column that we want to knock out. There's the multiple that we want to use, and here we actually take a multiple, this multiple of the ith row, and add it to the jth row, and to knock out the jth element in the ith column. And we do the same multiple of bi, add it to bj, and notice here AJI is the element we're trying to knock out, so that should be 0. So why do we set it to LJI? Well, we'll talk about that in a minute, but we're actually setting it to the negative of the multiplier. Well, it's really 0, and we won't forget that it's 0, and we're never going to use it. So it doesn't hurt to store anything we want there, but there's a reason for saving the negative of the multiplier we'll see in a minute. Now we're finished with the forward elimination and ready to do back substitution. And here's the back substitution. Solve for xn is just simply bn over ann, and then we go in reverse order, solving for xn minus 1 through x1, and we're through. Now if you analyze the amount of computer operations required by DLINEQ to solve the n by n linear system, we see that it turns out to be 1/3 n cubed multiplications. Now let's look at an example. Okay, here's a simple 3 by 3 linear system. We're going to not do any pivoting for the moment, and let's take minus 2 times the first row and add it to the second to knock this element out. We do that. That should be 0, but remember we're saving the negative of the multiplier. We took minus 2 times the first row and added it to the second, and we put the negative of the multiplier, which is plus 2. We put it there. I put it in parentheses to indicate that we know that's really 0, but I'm using that storage location in memory to save the negative of the multiplier. The reason for doing this, as we'll see in a moment, is it makes it much faster to solve other linear systems with the same matrix but different right-hand side. But anyway, it doesn't hurt anything to save the kind of a memento of battle. Remember how we knocked that element out, basically. Then we take minus 1 times the first row and add it to the third. There's the result. Again, that should be 0, but we put the negative of the multiplier, which was minus 1, and we save it there, even though it's really 0. Then we've got one more element to knock out, and we have upper triangular form. So now we need to take minus 3 times the second row and add it to the third to knock out the minus 6. We do that and put the negative of the multiplier there. And we have upper triangular system. We solve for x3, 5x3 equals 15, so x3 equals 3. Then we go back and solve for x2 knowing x3, and solve for x1 knowing x2 and x3, and we get the solution. But notice that at the end, after DLINEQ is finished with this matrix, these elements below the diagonal are all 0, but they're not really. We've saved the negatives of the multipliers there in case we need to solve another linear system with the same matrix. Okay, now we want to talk about the so-called LU decomposition of A, which is going to allow us to solve additional linear systems with different right-hand side and same matrix much faster. In fact, it'll be order n square instead of order n cube work. First, let's notice that every time we take a multiple of one row and add it to another, that's equivalent to multiplying on the left-hand side by a little elementary matrix. For example, taking minus 2 times the first row and adding it to the second is equivalent to multiplying by this matrix M21. The first and third rows don't change. The second one is replaced by minus 2 times the first row plus the second row. Then we took minus 1 times the first row and added it to the third. That's equivalent to multiplying by M31. Then we took minus 3 times the second row and added to the third row. That's equivalent to multiplying by this matrix. So essentially we had the linear system AX equals B. We multiplied on the left-hand side, the left and right-hand sides by this M21, which had the effect of taking minus 2 times the first row and adding it to the second. Then we multiply both sides by M31, M32, and we end up with an upper triangular matrix. In other words, A, if you multiply on the left by these elementary matrices, ends up being an upper triangular matrix, which you then solve. Then you solve the linear system using back substitution. But notice that this means that A is equal to M21 inverse, M31 inverse, M32 inverse times U. But the inverse of each of these lower triangular matrices is lower triangular, as we saw in the first chapter 0, and the product of lower triangular matrices is lower triangular, so this in parentheses must be a lower triangular matrix. So we found an LU decomposition of A, where L is actually the product of the inverses of these elementary matrices. And this is not trivial, but if you multiply it out in these examples, and in general this is true, turns out that the U is well, in this case it's this matrix, which notice the L. The L is a lower triangular matrix. The product of those inverses of elementary matrices gives you a matrix with ones down the diagonal and the negatives of the multipliers that were used to knock out the elements. In other words, when DLINEQ is finished with A, the U, it's saved the LU decomposition of A. The U is just sitting there, and L is a matrix with ones down the diagonal and the negatives of the multipliers used to knock out each element below it. So basically we have L and U just sitting there. And it didn't cost us anything extra, because all in the world we had to do was save the negative of the multiplier every time we knocked out an element below the diagonal. Instead of putting a 0 there, we saved the negative of the multiplier, and we end up with L and U both saved in compact form in the matrix A. So DLINEQ has essentially calculated LU decomposition of A. So what good is the LU decomposition? Well, if we have to solve another linear system, say AX equals C with a different right-hand side, but same matrix, and we already have the LU decomposition of A, then all we have to do is solve two triangular systems. We first solve LY equals C. That's a lower triangular system, which is only order n square work. And then we solve UX equals Y. That's the upper triangular system, exactly the same U as we used in the back substitution. So a total of order n square work, which is much less than the order n cubed normally required before you have the LU decomposition. So for example, with the same A matrix as in the last example, if we choose C to be this vector, then we solve LY equals C. We can do that by essentially forward elimination. In other words, now here we can solve for the Y1 simply by dividing -1 by 1. Then we solve for Y2, knowing Y1, then we solve for Y3. So it's forward elimination, forward substitution. And then we do the back substitution, and we get X. And it may not seem like a whole lot less work when doing by hand on a 3x3, but for a very large system, it's much less work on the computer. Now in the book there's another Fortran and MATLAB routine called DRESLV, which solves a linear system AX equals C, assuming that A has already been decomposed into its LU decomposition by DLINEQ. So this will be the A exactly as it comes out of DLINEQ, with the L below the diagonal and the U in the upper triangular part. And notice we're assuming that there's no pivoting here. So far we've assumed that no pivoting is necessary. In a minute we'll discuss what to do when you have to do pivoting, as you normally do. So here's the entire routine. The first part has to do with pivoting, which we'll skip for now. Let's assume no pivoting is done by DLINEQ or DRESLV, that no zero diagonal elements appear. And here is you can call it forward substitution or forward elimination, but the key is that you don't have to do the forward elimination on the matrix A. It's already been done. We know what the final U is going to be, and we know what the multipliers are. They've been saved. See, AJI has been saved, the negative of the multiplier that was used to knock out each element, and all we have to do is apply that to the vector C. And so it's only a double nested do loop here, so it's only order n square for the forward elimination. Basically we're solving LY equals C, or Y equals L inverse C, and essentially doing the forward elimination exactly the same as DLINEQ, except we're simply skipping. We don't need to take a multiple of the ith row of A and add it to the jth row. We simply take a multiple of the ith element of C and add it to the jth element of C, and we don't do anything to A because we already have all the multipliers and we have the final upper triangular form. Then we do the back substitution. That's essentially solving UX equals Y, and this is exactly same as DLINEQ because it's the same upper triangular matrix. So forward elimination is only order n square, whereas DLINEQ it was order n cubed. Back substitution is order n square in both cases. So the total work has been cut from order n cubed to order n square if you already have the LU decomposition. So far we've assumed that no pivoting is necessary, but often it is. In fact, DLINEQ will nearly always do some pivoting, uses partial pivoting strategy. So let's go back to the DLINEQ subroutine. Notice at the very beginning it sets up a permutation vector iperm of k equals k. So iperm vector starts out 1 through n, and then in DLINEQ every time we have to switch two rows, we switch the corresponding elements of iperm. So basically we keep up with all the permutations we do during DLINEQ, and then if we apply DRESLV to solve another linear system with the same matrix, what do? Well, we have not only the LU decomposition of A, but also this permutation vector that has kept up with the row switches that we did. Now, if you think about it a minute, you'll see that once we know what permutations we had to do, if we had known that at the beginning, we could have permuted those equations, those rows in the matrix A and the right-hand side B at the very beginning. Before we started, we could have done all the permutations then, and then if we proceeded with Gaussian elimination with partial pivoting, we would end up doing no pivoting at all. So basically you can imagine that we're solving AX equals B. If we multiply by a permutation matrix P, which switches the rows of A and the corresponding elements of B, then you don't have to do any further pivoting. So you're essentially finding the LU decomposition not of your original A, but of PA. So now if you're using DResolve to solve another linear system with same matrix but different vector C, then DResolve is going to do all the permutations at the beginning because it does know how the rows are going to end up. And so we essentially are multiplying both sides of AX equals C by a permutation matrix P, which simply switches rows and elements of C. And then we find the DLINEQ finds the LU decomposition of PA. So now we simply do the permutations to C, and then we solve LU x equals PC in the usual way. So if we go back to DRESLV, you'll see that that's exactly what it does. At the very beginning, we skipped this earlier, it simply switches the elements of C using the permutation vector iperm, which is passed from DLINEQ, which kept up with what switches were done earlier. Now it does all the switches to C. No need to do them to A because we already know how A is going to end up as L times U. And so we do the row switches on C to begin with, and then all we have to do is the forward elimination or forward substitution and the back substitution, and we've got our solution. Now, does it happen often in applications that we have to solve several linear systems with the same matrix? Yes, it certainly does. For example, in analyzing effect of different loadings on a structure, the structure doesn't change and the only thing that changes are the loadings, the wind or earthquake, whatever is acting on the building, then you're going to be solving several linear systems with different right-hand sides and the same matrix. So it is important in applications.